this example, we're going to use the shell method to find volume. But contrary to the last video, in the video that preceded this, we're going to rotate about the x-axis, which is going to change the dynamics of our integral setup just a little bit. So we're still going to find the volume of the solid of the region bounded by the curve, which is given below, y equals the square root of x. It's bounded by the curve, the x-axis, and the vertical line x equals 4. And this region is going to be revolved about the y-axis to generate a solid. So let's look at what this graph or this shape looks like, what our region is. So we have the same curve that we did in the last video, but what you want to notice is that we are going about the x-axis here, which is going to create a slightly different shape. It's kind of more of a mountain on its side, okay? A parabolic type cone, if you will. So since we are going about the x-axis, you'll notice my radius is some unknown vertical distance. So my radius is going to be y. And then my height, my shell height, which is always parallel to the axis of rotation, my shell height is going to be this curve here. Right, so this curve represents the height. And I want you to notice my curve is y in terms of x, but since we're using the shell method about the x-axis, we need x in terms of y. And then we have to think about how to measure this height. All right, the height is a difference of the outer minus the inner. So my outer part of the radius is 4, and the inner part of my radius is going to be y squared. All right, when we integrate with respect to y, you're always going to say right minus left if you need to subtract curves from each other. Just like if we were going, or rather working in terms of x, we would say the above curve minus the below. But here we're working in terms of y, so it's going to be right minus left. All right? So the way I would set this up is I would say that my volume is some integral from c to d. We've got 2 pi, the shell radius. The shell radius in terms of y is y, times the shell height. And the shell height is going to be 4 take away y squared, integrating with respect to y. And my c and d value, my upper and lower, are going to be 0 to 2. Because I'm dealing with y, I am choosing that 0 and 2, my bounds of integration, on the y-axis as opposed to on the x-axis. And you could have worked this problem to find the same volume using the disk method, and that might end up with a little less work for us. I just want to show you that both methods work. It's just sometimes we need to determine how to choose which method. And also you need to know how to set it up either way, because sometimes there's definitely a benefit to choosing one method over the other. So once we've set this up, now that we know how we're going to have it set up, let's run through our integration. I'll pull my 2 pi out front. I've got the integral from 0 to 2. I will distribute here, which is 4y minus y cubed. Integrating with respect to y. So I've got 2 pi. That integral would be 4y squared over 2 minus y to the 4th over 4. Used the power rule. And we'll evaluate from 2 to 0. So that is 2 pi. We have 2 times 2 squared minus 2 to the 4th over 4 minus 2 times 0 squared minus 0 to the 4th over 4. So that last piece there, that's just going to turn to 0. We don't need that. And we just need to calculate this beginning part, which running through this, I have 2 pi, 2 times 2 squared is 8, minus 16 over 4 is 4, or 2 pi times 4. 8 pi represents the volume of this region. So I'd like to summarize our shell method for us. And here we have our summary. So regardless of the position of the axis of revolution, whether or not it's horizontal or vertical, the steps are always going to be the same, the steps that we implement. So we're going to draw our region and sketch a line segment across it parallel to the axis of revolution. All right, that will give us the shell height, and then the distance from the axis of revolution will give us the radius. Depending on the variable, we determine our limits of integration, and then we would integrate. It's always going to be 2 pi radius times height. And so now we've basically used both of these methods, our shell method and our washer method. And the washer method is just kind of a more formal description or definition of the disk method. And for some regions, both that washer and the shell method are going to work well for generating that solid that's created by revolving a region about some coordinate axis, but that's not always the case. What you need to remember is when the region is revolved around the y-axis, for example, and if you're using washers, well, then you need to integrate with respect to y, and it may not be possible. All right, sometimes it's not easy to express your integrand in terms of y. And so in such a case, the shell method is always going to allow you to integrate with respect to x instead. And we generally do a lab in class where we look at the differences between our washer and our shell method. So I've included my hints here that kind of help us when we're thinking about or trying to determine which method to use. If we have y in terms of x, if we're going about a horizontal line, use the washer method. Y in terms of x about a vertical line, you might want to use the shell method. And if you have x easily in terms of y, then about a horizontal line we would use shell, and a vertical line, then we would use the washer. All right, and I've kind of put our washer and shell methods there for comparison. So please, feel free to email me if you have any questions about these methods.